All right, well, good morning, everybody. I'm going to continue lecturing about Majorana-based quantum computation. My plan for today is to finish going through the Kitaev chain. Then I'm going to describe some experimental blueprints that allow you to realize the physics of the Kitaev chain in realistic devices. And then I will turn to the key problem of how you actually detect Majorana modes in experiments. So let me start by just reviewing some stuff that we did last time that will be useful for what we do today. So at the beginning of last time, I introduced Ising non-abelian anyons in a rather general way. I mentioned that there are these three key defining characteristics that those kinds of particles exhibit. First of all, as you start populating them into your system, one gets a space of locally indistinguishable, robust, degenerate ground states that actually grows exponentially with the number of anyons. For Ising anyons, the ground states grow like 2 to the number of anyons divided by 2. Second defining characteristic is that if you perform an adiabatic braid of 2 of these non-abelian anyons, your system gets rotated within the degenerate ground state manifold. And finally, when you bring pairs of non-abelian anyons together, they exhibit non-trivial fusion rules. They can either annihilate each other or produce a fermion. So that's the non-trivial fusion rule for Ising anyons. All right, so after that, we delved into the Kitaev chain, which is some very minimalist model in which you can recover all of those maybe a little bit mysterious characteristics of non-abelian anyons. So here's the Hamiltonian that we were looking at. We have spinless fermions described by these CX operators. There's a chemical potential, nearest neighbor tunneling, and a nearest neighbor pairing term. So by looking at this Hamiltonian momentum space, we were able to deduce the rough phase diagram. So here's mu over t. For mu over t less than -1 or greater than +1, we got a trivial superconducting state. In between, we got a topological superconducting state, and these gapped phases are separated by a critical point. So we wanted to then get a little bit deeper understanding of the properties of those gapped phases, and for that purpose, it's very useful to employ a Majorana representation. So that's what we did next. So we decomposed our spinless fermion operator Cx in terms of 2 Majorana operators, gamma b and gamma a, which are kind of like the real and imaginary parts of that original fermion operator. So those Majorana operators satisfy the properties shown here. They're Hermitian, a squared of 1, and they anti-commute with each other. As I mentioned last time, it's really important to realize that there's no occupation number associated with an individual Majorana. Only pairs of those guys have well-defined occupation numbers. So I then cherry-picked the Hamiltonian a little bit. I decided to set delta equal to t. That just happens to be a particularly convenient limit because a lot of the physics, particularly of the topological phase, just jumps out at you if you specialize to that limit. So if you rewrite the Hamiltonian in this Majorana representation and set t equals delta, then this is what you get. So here's the chemical potential term. That couples gamma b and gamma a on the same site, and the hopping and pairing terms couple gamma b and gamma a on adjacent sites. So there's a nice pictorial representation of the Hamiltonian when written in this basis. So here, each of these blocks represents the original Cx fermions, which I decompose into a pair of Majoranas. So mu basically wants to dimerize the Majoranas by coupling Majoranas within a given box. So that favors a state that actually has no entanglement with neighboring sites of the chain. So T wants to exhibit, so T favors a shifted dimerization pattern where this Majorana couples to the next one over in the chain, this Majorana couples to the next one over in the chain, and so on. So the most interesting case corresponds to taking just mu equals 0 and then taking T finite. In that case, we get a very simple dimerization pattern. So these inner Majorana modes all couple to another member of the chain, and they all gap each other out. But we see that at the ends of the chain, there are these unpaired Majorana modes, which I call for shorthand gamma 1 and gamma 2. So those are zero energy modes of the system. They don't appear in the Hamiltonian, and they trivially commute with the Hamiltonian, and therefore acting with gamma 1 or gamma 2 doesn't change the system's energy. Okay. So what we did next is we reassembled those edge Majorana zero modes into a new ordinary fermion. d by taking gamma 1 plus I gamma 2. So I call that an ordinary fermion because it has a well-defined occupation number, just like the original C operators that we had up there. But of course, this is a highly non-trivial object. It's non-local because it arises from a superposition of Majorana modes that can be separated by arbitrary distances from one another. Okay, so if you look at d dagger d, then that's just 1/2 times 1 plus I gamma 1 gamma 2. So since gamma 1 and gamma 2 commute with the Hamiltonian, so does d dagger d. And the occupation number of that non-local fermion can either be 0 or 1, and that occupation number has no effect on the system's energy. All right. So therefore, we have a ground state degeneracy. I labeled those ground states 0 and 1, where the 0 and 1 corresponds to the occupation number of d dagger d. Okay. So those two ground states are different from one another in the sense that they carry opposite fermion parity. Okay, so this one might have, let's say, overall even number of electrons, and this one would have overall odd number of electrons. So one thing that may be useful for later on, the two states where d dagger d is 0 or 1, in terms of Majorana operators, those correspond to states where this quantity I gamma 1 gamma 2 is plus or minus 1. So if that quantity is minus 1, you get d dagger d is 0. If it's plus 1, then you get d dagger d equals 1. Okay, so that'll come in handy next time. Okay, so after that, I made a few more, well, I guess one more comment. Yeah, please. Whether t is plus or minus, it makes no difference. Yeah, you can check. I mean, the structure of the ground states will change somewhat, but the existence of zero modes and the fact that the bulk is gapped, that doesn't matter. Okay, any other questions? All right. So I think the one other comment I had made last time pertained to what happens when I move away from this cherry-picked limit. So if I take mu not equal to delta mu not equal to 0 and t not equal to delta, we still have almost zero energy modes. So the gamma 1 and gamma 2, their wave functions won't be perfectly localized to one site, unlike what we saw in those pictures. Instead, they'll decay exponentially over some length scale c into the bulk. Okay. And so since there's some exponential decay into the bulk, those Majorana modes will have some tiny overlap, which leads to some residual splitting between those 0 and 1 states. But that residual splitting goes like e to the minus L over c. And so if L is much larger than c, then for all practical purposes, you can think about this as being 0. All right. Yeah?
So it's about this non-local fermion. I can see the operator is useful in that limit. But if you relax the condition that you can write everything in terms of Majorana operator, can you still define something analogous to d dagger d, like for these other classifications?
Yeah, okay, so if you take the more general notion of gamma 1 and gamma 2, which are approximately zero energy modes that are not localized to one site but have this exponentially decaying wave function, then everything I wrote here holds exactly as before. So one.
I'm trying to ask, like, if there is a representation equivalent to d dagger d, but it consists of lots of local operator. So here it's really non-local. I'm just curious if there's a way to define it in a really local way, or start with some.
So this degeneracy will always be, in some sense, non-local, as long as the separation between gamma 1 and gamma 2 is much larger than the exponential decay length. Right, that's all you need. Yeah.
But can you please make a comment about interactions?
When you say interactions, what do you mean?
So like
Perturbations?
If you include interactions for these fermions, for the original fermions, how much of this survives?
In fact, that's my very next comment. So, very timely question.
I saw you both.
Nice. Okay, so yeah, so now I want to actually what I would like to do now is make a hopefully pretty direct connection to Ising anyons. And one of the defining characteristics of Ising anyons is robustness of that degeneracy and local indistinguishability of those ground states. So in fact, this approximate ground state degeneracy is indeed robust to arbitrary local perturbations, including interaction terms. And how can I confidently assert that? Well, it's really the physical separation between gamma 1 and gamma 2 that underlies this conclusion. If you want to split this degeneracy, then you have to couple gamma 1 to gamma 2, but imagine they're miles away. Any term that does that has to be non-local. Right? So by default, due to the physical separation, we have some intrinsic resilience of that degeneracy. Closely related property is that those two ground states are locally indistinguishable from each other. So you might, for instance, try to identify whether you're in the state 0 or 1 by performing a local measurement in the vicinity of, let's say, either gamma 1 or gamma 2. But actually, there's no information whatsoever about the state encoded in an individual Majorana, right? So in order to know which state you're in, you have to know about something involving the product of those Majorana operators. But again, they're separated by miles away from each other. And so local measurements can't reveal that information. Another maybe useful way to view this is in terms of the physical distinction between 0 and 1. Right? These carry opposite fermion parity. And if you want to know whether your system has, let's say, total even or total odd number of electrons, what you'd have to do is count up the number of electrons in the entire system, take mod 2, and then you can deduce that information. But that's obviously not something that you can locally infer. All right, so far we're starting to make some connection to Ising non-abelian anyons. So next I'd like to ask, what exactly should I think about as the Ising enyon in this Kitaev chain? So maybe that's not so obvious. So the thing that you should associate with an Ising enyon is actually the endpoint of a Kitaev chain, or more generally the domain wall between a topological and trivial phase of the Kitaev chain. Those mimic Ising non-abelian anyons. So what about the zero modes? In the early days of this problem, condensed matter physicists, including myself, would kind of abuse notation and call the zero modes particles, and that's actually nomenclature that one should avoid. Those zero modes are not particles in any sense. They're really the internal degrees of freedom that encode the unusual ground state degeneracy that Ising anyons generate. So this is just semantics, but I think it's a useful thing to keep in mind. Okay, so what about the exponentially growing ground state degeneracy? So we can recover that as well. There's no reason that I need to consider a system that has just a single pair of Majorana zero modes. So let's consider a more general situation where we have a wire that has a topological phase in one region of space and then a trivial region, then another topological region, trivial region, and so on. Okay, so in this way I can create an arbitrary number of Majorana modes. And every pair of those Majorana modes is similarly going to give me a factor of 2 in the ground state degeneracy. So these things are all Ising anyons, Morley. Okay, so since each pair gives us 2 states, the counting of the total number of ground states would go like 2 to the number of anyons over 2, exactly as for Ising anyons. So that takes care of our first bullet point for Ising anyons. The second pertains to non-abelian statistics. So that might seem a little bit more dubious because exotic exchange statistics is often viewed as a phenomenon unique to the two-dimensional world. But in fact, we can actually meaningfully braid these non-abelian anyons in these wires if we move away from strict one-dimensionality in the smallest way possible. So for example, suppose that I add an extra vertical leg to this wire. So now I'm creating some kind of wire network, and I can exploit these wire networks to braid in a meaningful way. Imagine that I want to braid, let's say, these 2 Ising anyons. So there's a very simple protocol that I can do. I can imagine first taking this 0 mode and dragging it down to the bottom end of that vertical leg. Then I can move this 0 mode over to the left, and then I can complete this exchange by moving the guy that was down here back up and to the right. So that's a perfectly well-defined braid. And maybe I should comment on how one can actually move these domain walls as a matter of principle. So if we go back here, if I want to toggle between topological and trivial superconducting phases, I can just change the chemical potential, right? And so if you imagine being able to locally change the chemical potential in different regions of your wire network, then I can systematically move the position of these domain walls to my convenience. Okay. So it might not be how you want to do things in practice, but that's at least a conceptually simple way of doing things. Yeah?
So should it be obvious looking at the Mateo chain model that we have Ising anyons on the ends of these, or is this sort of...
No, that's what I'm trying to argue here. Right? So I'm trying to go, so my strategy now is to go through those 3 defining features and try to show that there's indeed some semblance of Ising anyon-like physics that's contained in this model. So far I think we're partly there, right? I took care of point 1. I argued, I think on pretty general grounds, that we had a space of locally indistinguishable, robust ground states that gave you the same counting as expected for Ising anyons. So now I'm on point 2, and then I'll eventually recover fusion. Yeah?
It's a question about the Symmetry class in temporal way. What is the class here for PIHM? Is like supporting Z2 or Z?
Well, okay, so that's a somewhat ambiguous question. So when I wrote down this Kitaev chain, I didn't have in mind any other symmetries beyond just global Z2, which you can't break. So when we discuss symmetry class, we should allow for arbitrary perturbations that are consistent with a given set of symmetries which you want to impose. So if this particular set of terms that I wrote down also has a time reversal symmetry which squares to +1, but the ... dots that I imagine being allowed in my physical system would break that symmetry. So I think there should be a Z2 invariant here rather than a Z.
So
Yeah.
I imagine the first operation, moving the domain wall down. Is there going to be like another domain wall, like an intersection? Is it like...
Okay, so let's see. So the so that's what I had after step 1.
Right, yeah.
So this isn't really a domain wall. This is just, I think you should think about this as being just a topological superconductor that's kind of bent 90 degrees.
Okay, so even though there's some kind of interface thing between...
Yeah, that doesn't matter. I can always introduce trivial phases without doing anything.
How do I do step 2 for
Okay, so step 2, this is where things are a little bit tricky. So I would want to, let me do this in 2 steps. So first, let me move that x over here. All right, so now I have a kind of peculiar situation. Well, it's a funny thing. So if I have, maybe it's convenient to kind of break this up a little bit. So let's imagine that I have 3 Majorana modes that are sitting very close together. So when you couple those 3 Majorana modes with arbitrary couplings, 2 of them kind of get pushed out to finite energy, but if the third, one of them has to survive on very general grounds. You can't take an odd number of 0 modes, hybridize them together, and kill everything. One of the 0 modes has to survive. So that's what I was left with at the interface. All right, so now I want to move this over. And so basically I'm going to nucleate a trivial region inside of here to do that. And that basically leads to this configuration. Okay, and then I'm basically done after that.
Do you mean you fuse the 2 to the vacuum? 2 over 3?
Yes, that's what you should imagine doing. Okay, so I have a well-defined way of exchanging these Ising-like anyons, even though I'm using one-dimensional systems. Now, if you were to start before the exchange in one of your degenerate ground states, after the exchange, you would indeed non-trivially rotate your system within that ground state manifold. Now, let me just give you some intuition for why you might expect something non-trivial like this to happen. So remember that these Majorana 0 modes are kind of like half of a fermion, half in the sense that they're you need to superpose 2 to get an ordinary fermion. So when I exchange these 2 guys, I'm exchanging half of one fermion with half of another fermion, and that kind of naturally will rotate your system in a very non-trivial way. Okay, so which is fundamentally different from if you exchange full fermions, which we know has to give you just a minus sign. All right, so if you actually want to know what this braid matrix is and derive it, at least in this setting, it's a non-trivial exercise. I'm going to give you a homework assignment, though, that there is actually a way of deducing the general form of that matrix with almost no work. So I won't do this in real time, but I'd be happy to discuss after. So if you swap a pair of Majorana modes, let's say gamma A and gamma B, then on general grounds, the braid matrix has to have this form. And the only thing you need to argue this is some notion of locality and conservation of global fermion parity. Okay. So I think this is a very hard homework assignment, but if you view it from the right way, it's like a 1 or 2 line exercise. So just think about it, and then we can talk about it later on. Yeah.
So I'm a little confused why I should think of this as this exchange statistic. So if it was like a boson or a fermion, when I swap 2 particles, the actual wave function doesn't change. It's the same state, it just acquires a phase. Whereas here you're saying that it actually flips between physically distinct ground states when you exchange particles, and so that's not the same wave function that it was before. So it's not like fermions where it just picks up a minus sign, but this contributes to important interference effects. It's actually causing a transition akin to like...
That's the amazing thing of non-abelian anyons. Right? It's a very counterintuitive thing. So, of course, if you have distinguishable particles, then if you exchange them, it's no surprise that you would get a different state. But here, these are indistinguishable particles, yet your system gets rotated within some subspace of your Hilbert space. So maybe it's useful to think about this from the point of view of adiabatic evolution. If you had a unique ground state and you were adiabatically evolving your Hamiltonian, then adiabatic theorem tells us that you just follow the instantaneous unique ground state, and there's no chance of getting to a different state. But here it's not obvious that you should end up in the same state that you started with. We have a degenerate manifold of states, and so adiabatic theorem doesn't restrict actually where you end up at the end of the day. The magic here is that not necessarily that you get rotated within your Hilbert space, but that rotation is rigid, right, and doesn't depend on details of how you perform that adiabatic braid. Yeah.
Are you missing an I in its way?
I'm not missing an I, so maybe it's useful to write this as put two I's in there, right? So this is the thing which is like a sigma z. Yeah.
So that if I swap the A and B Majorana modes, that's the
Yeah, sorry. Is there another question? Okay. Yeah, so provided that you're only involving a pair of Majorana modes and not other guys. Okay, so this is actually important. This is related to the set of gates that you can actually generate by braids of Ising anyons. Yeah.
So with that operator, the state rotate from zero fermions to 2 fermions. Is that right?
No, I mean, so this is a statement that's kind of independent of which states you're in. So in general, I started from a configuration where I might have many of these Majorana modes, right? So I could have an enormous amount of ground state degeneracy, and you start with any state in that manifold, and after you apply a braid, then you end up with a new state that's determined by that braid matrix.
But it's a rotation of just 0, 1 space of those two of the two Majoranas that are involved that you exchange.
That's right, yeah, but I guess the important thing is that if I have many Majorana modes, then this sector, these two states can in some sense be entangled in a non-trivial way. But indeed, actually that's part of the locality assumption that you have to make in order to derive that the exchange only involves the pair of Majorana operators that you've braided. You can imagine bringing all the other ones infinitely far away. Yeah.
So this is a Majorana mode specific thing. It's not an Ising anyon general thing. Is that right? This unitary that you
This is pretty general, so up to an overall phase. So the overall phase I actually don't care about, and so I'm ignoring. But technically, there's actually different kinds of Ising anyons, which would be characterized by different values of the overall phase. But that overall phase is not even defined in this particular context. So, yeah.
Sorry, can you say a bit about how you change the chemical potential to implement this step 2?
Yeah, so imagine, again, this is probably not what you would want to do in reality, but suppose that you had some array of locally tunable gates appended to adjacent parts of your wire network. So by tuning, let's say, the potential on this local gate here, I can toggle whether this region is in a topological or trivial phase, and therefore shuttle that Majorana. Similarly, I can then adjust the next gate and so on. And so if I have the ability to spatially control locally control the chemical potential, I can locally tune whether a given part of the wire is topological or trivial, and that's the only degree of freedom I need in order to perform these kind of braids.
But I was thinking specifically for the second step. Is it like you increase? I guess imagine you're increasing the chemical potential to move it to the left, like you want.
It's exactly the same thing. I mean, in all those steps, all I'm imagine doing is being able to locally change.
Yeah.
Yeah. Yeah.
So, last lecture you talked about not having any
But like in this situation, suppose you're really exchanging those two, and the other ends are far away. I mean, does non-trivial U that you generate under that exchange tells you that you might have started in the 0 fermion, and you're not going to create 1 fermion.
No, yeah, you can't do that. So maybe it's useful to,
So what's happening?
yeah, okay, so suppose that I just had 4 Majorana modes. Okay, so then I have basically two zeros and ones that I can specify. So I have a total of 4 states. All right, so the top 2 states have total even parity. The bottom 2 states have total odd parity. If you were to perform an exchange, you can rotate your system within the even parity sector or within the odd parity sector, but you will never mix between these 2 sectors.
Right. I mean, I guess, yeah, so that's what you explained last time. So I guess I'm asking, if I take the other 2 Majoranas, the 2 ends.
These 2 guys here?
Yeah.
Uh-huh.
Set them very far away, and then now just perform this exchange very locally on the 2 that you have the path 1, 2, 3. You're saying the occupation of the other 2s will change to be consistent with total fermion parity, even though they're very far away.
Well, it depends on the state that you start from. Okay, so this is maybe a good point. So when I wrote 0, 0, and 1, 1 here, I meant, I didn't say this, but I implicitly was thinking about one of those zeros and ones corresponding to the fermion made of these 2, the other being made of these 2. But that's a basis choice. I didn't need to choose that convention. So if I were to alternatively define, let's say, a 0 tilde, 0 tilde, and so on, those tilde occupation numbers might correspond to, let's say, fermion made out of those 2 guys and a fermion made out of those 2 guys. So if you initialized your system, let's say, into the 0 tilde state, and then performed an exchange of the inner ones, you're just going to stay in that same state and maybe acquire a phase factor at most.
Oh, I see.
But it's a basis dependent question. Yeah. Okay, any other questions? Yeah.
What's the difference between definition of Ising anions and Majorana modes? Like, is it just an overall phase difference?
So that's what I was trying to allude to here. So, maybe a kind of silly analogy would be if you think about, so calling, let's say, a Majorana mode an Ising anion is kind of like calling an engine a car. It's not exactly the same thing. The Majorana 0 mode is kind of like the engine that gives the Ising anion its interesting characteristics, but the Ising anion is a somewhat more general entity. I don't know if that's helpful.
So it cannot be called as a typo, right?
I wouldn't call the 0 mode a particle. I wouldn't call it a quasi-particle. I wouldn't call it an Ising anion. It's just it's some kind of internal degree of freedom that is necessarily bound to an Ising anion in order to give it the characteristics that it has.
It gives you the same grade metric and fusion rules and so on.
Well, you can understand very efficiently a lot of the properties of Ising anions by understanding the properties of those 0 modes. But, ultimately it's semantics, so I don't think it's worth spending too much time addressing that point. But as long as you understand exactly, the physics, I think what you call what, you can call it a bird if you want. I don't know, whatever you want. If you get the physics right, it doesn't matter. All right. Yeah.
So about the basis choice, so if we write on the basis on the left, it seems, for example, like 0, 0 plus 1, 1 looks like an entitled state. So when you write it as 0 tilde, 0 tilde, it just looks like a product state. So could you elaborate on what the nature of the basis characteristic is? Because naively it seems to be these characteristics.
Well, I'm not quite sure I know what to say. I mean, if you, there's a well-defined basis transformation that one can apply to go from any definition of fermions to a different definition of fermions. And there are, I think they're so-called F symbols that relate different bases, technically part of the topological quantum field theory. I don't think I have anything particularly useful to say about that, unfortunately. But okay, so I wanted to briefly comment on one somewhat sad fact about Ising anyons, which is related to this this braid matrix. So if you're only allowed to allow yourself to braid and do nothing else, you don't actually generate a universal gate set. That's not a general statement about non-abelian anyons. It's a specific deficit of Ising non-abelian anyons. So maybe you can even kind of see that just by staring at this braid matrix. You know, this is like a sigma z, so e to the plus or minus pi over 4 sigma z is like a pi over 2 rotation. And there's no way that you're going to cover the full block sphere by just applying pi over 2 rotations of your qubit. So there's limited gates that you generate through braiding alone. If you allow yourself to also perform measurements, then you can actually get an entangling gate. But you still have a missing phase gate that you need to include in order to achieve computational universality. The good news is that missing phase gate, although you can't quite do it in a fully protected fashion, the error tolerance that gate comes with is rather mild, and so you can have a rather noisy phase gate and correct it pretty efficiently. So it's that's anyway. This is what nature is likely to give us, at least in the short term, in terms of topological quantum computing hardware, and that's what we have to wrestle with. Yeah. Replace the 4 by an 8. That's it. Yeah. Okay. All right. So now I've recovered points 1 and 2. So let's discuss fusion.
But it's still just rotation on z-axis.
Oh well, it depends. Because I have arbitrary. I mean, I didn't tell you exactly which. It's for any gamma A and gamma B. All right, so let's go back to a simpler geometry where we just have one topological superconductor with originally very well separated Majorana modes that give us basically a perfect degeneracy, again modulo exponentially small corrections. You can now imagine taking these two ends and then bringing them together. Okay, so these dashed lines are trivial regions, and I just have a little tiny patch which is quote-unquote topological. It's not really well-defined topological phase anymore because I'm assuming this is sufficiently small so that it's really not a sharp distinction. So once those Majorana modes come together, they hybridize with each other, and they form a fermion that costs you finite energy to occupy. So this originally twofold ground state degeneracy will split. Now, if your system lands in the lower state, then that corresponds to the identity fusion channel. And so if you actually just remove that entirely, then you would just end up in the ground state of the system, and you have no trace of the anyons that were there to start with. And so that's naturally should be associated with those anyons annihilating each other. On the other hand, you might end up in an excited state where there's an extra finite energy fermion that's localized to that region, and that corresponds to the psi fusion channel. So this is a way of recovering non-trivial fusion that I mentioned in a more cryptic way previously. All right, so that's the end of my discussion of Kitaev chain. So in the interest of time, I decided to skip going through two-dimensional topological superconductors. I'm kind of sad about this, actually. I think it's really neat physics, and that's not obviously irrelevant to the story in terms of experiments and so on. If you're interested, you can come talk to me later about that. I'll also post these notes online at some point.
What where you end up in channels, what does that depend on?
It depends on how you initialized, well, what state your system is in. It's kind of a tautological thing to say, I guess. But
If you like literally just in the originally trivial state with no fermions and things like that.
yeah, so maybe this is worth going through in a little bit of detail. So suppose that, so this question is history dependent. Maybe that's a general thing I can say. Imagine that you started from a trivial phase, and then you pulled out a pair of Ising anyons and then brought them to the other end. Okay. Now, if you go through this step, it's clear that you're just going to land in the ground state. Okay. But you could have imagined doing something a little bit different. So let me make this slightly more complicated. Let's add a second topological superconductor. So imagine you did this, you initialize your system, and maybe initialize those guys as well by pulling them out of the vacuum. Then you could imagine braiding those two, and then fusing. Okay, so in this case, that braid would have rotated you in your degenerate Hilbert space, and then there's actually a probabilistic, you're in a superposition of those two fusion channels, and I think for that specific braid that you would do, half the time you would end up down here, half the time you would end up here. And I think if you did a double braid,
Because now you're annihilating with the other zero node.
yeah, essentially, that's right, yeah,
And that changes the sign.
yeah. Okay. All right, so if there's no more questions about Kitaev chain, I'm now going to turn to question of experimental realization. For the Kitaev chain? Well, the Kitaev chain was unsurprisingly invented by Kitaev. Well, invented, it's kind of a funny thing to say, but because it's really just the Ising model and they're viewed on a different basis. But the seminal work outlining all of this was in a 2001 paper by Alicea Kitaev. It's in Physics Uzbeki or something like this. Do you know this journal? It's a Russian. But anyway, you can find it on the archive. The paper is called something like Unpaired Majorana Modes, something like this.
But even Majorana representation predates Kitaev, right? Solution of the answer.
Oh, sure, yeah. So I think what Kitaev really did was show us that there was something topological and protected. And he also, did more than just what I've shown you here. He invented so-called fractional justice effect, which we'll go through next time. It's a really classic paper, even though you can reinterpret it all in Ising model language. All right, so if you want to have a realization of Ising anyons in topological superconductors, then what you really need is a realization of a one-dimensional spinless superconductor. So that's really the essence of what makes a Kitaev chain special. And when I say spinless, I just mean a system that has just a one-dimensional system that has just a single pair of Fermi points in the band structure that you then apply pairing to fully gap out the system. If you do that, then you're automatically in a topological phase that's smoothly connected to the Kitaev chain. All right, so there's good news and bad news at this point in our story. The good news is that superconductivity is a by now very mature subject. It's more than 100 years old, and we have thousands of superconductors at our disposal to use to search for such phases. The bad news is that you can look amongst that list of thousands of superconductors and ask which of them gives you the physics of the Kitaev chain, and the answer is almost certainly none of them. So there's three basic challenges that are involved, which I'd like to highlight for you. So there's the obvious fact that we live in 3 dimensions. And so this is not such a big deal. We make one-dimensional structures all the time, but it restricts the class of materials that you have at your disposal. Second is the inconvenient fact that electrons carry spin. So if you look at the band structure, energy versus momentum for typical materials, you usually have both spin up and spin down branches that are degenerate with each other. And in the ground state, typically both of those branches will be partially occupied. So if you want to achieve something that looks effectively spinless, you need to kick out basically half of those states from, and just have a single pair of Fermi points rather than 2. The third challenge is that among the many thousands of superconductors that we have at our disposal, almost all of them arise from the formation of spin singlet S-wave Cooper pairs. And that makes solving problem 2 quite difficult. So the naive thing you might want to do to solve problem 2 is just spin split those bands. So make the spin up branch higher in energy, spin down branch lower in energy. But then you are going to suppress the ability for your system to form spin singlet Cooper pairs. Right? Because most superconductors, spin up and spin down, are crucial to the formation of superconductivity. Okay, so that's what we need to figure out how to solve. If you want to solve 1 or 2 of those challenges, it's not a problem, but solving all 3 at the same time is tricky. So fortunately, we now know of very efficient ways of basically engineering the physics of one-dimensional spinless superconductors using completely garden variety materials that have been around for ages and can be studied in a variety of different experiments. There's probably of order 100 papers revealing various different strategies to engineering topological superconductors. Almost all of them follow a common 2-step recipe, so I'm going to just give you that 2-step recipe rather than summarizing 100 separate papers. All right, so the first step is basically aimed at solving these first 2 challenges in a way that makes solving the third trivial. Okay. All right, so essentially I want to find a nice realization of just one-dimensional quote-unquote spinless modes, and then we're going to deal with the superconductivity in step 2. Okay, so one option is to use the edge state of a 2-dimensional topological insulator. I don't know, in this community, do people know what topological insulators are? Okay, so some people, yes, some people know. I'll tell you all you need to know about topological insulators for this purpose. So 2-dimensional topological insulators are, as the name suggests, they're topological phases of matter that are insulating in the bulk but have unusual edge states. Right? And the structure of edge states in a 2-dimensional topological insulator is as follows. So you have a set of clockwise circulating modes, which let's say correspond to spin-up electrons. and a counterpropagating set of modes that carry spin down. Okay, so that's interesting band structure. You know, if you those spin up and spin down branches are related to each other by time reversal symmetry. If you look at the energy versus momentum, you have let's say a right mover which carries spin up, and a left mover that carries spin down. So the beauty of this band structure is that it doesn't matter where I put my chemical potential. I always have just a single pair of Fermi points. Okay. But importantly, as we'll see in a second, you know, the fact that you have both spin up and spin down branches is a great virtue. Okay, I hope no one's confused by my calling this spinless. Obviously, it's not spinless in the sense that I have an active spin degree of freedom, right? So the carriers here are spin up, carriers here are spin down, but it's effectively spinless for the purpose I care about, in the sense that we have just a single pair of Fermi points rather than two. Right? Okay, so that's one option. We can either use a two-dimensional topological insulator boundary, or, by the way, this idea was due to Fu and Kane. I think they're really the first innovators of this idea of engineering topological superconductivity. The alternative is to break time reversal symmetry, which I'll just indicate by that script T, in 1D systems with spin-orbit coupling.
The question.
Yeah.
The boundary is gapless.
The boundary is gapless. Yeah.
How is it a superconductor if it's gapless?
Oh, I didn't say this is a topological. It's not a topological superconductor. Right? But I'm going to use those unusual edge states to create a topological superconductor. But I'm only halfway there. So it's just step one. Okay, so as an important example, we can consider one-dimensional wires with so-called Rashba spin-orbit coupling. Subjected to a magnetic field. So the idea I'm following now here was due to Roman Luchin, Jay Sao, and Shankar Das Sarma, along with Yuval Oreg, Gil Raphael, and Felix von Oppen. So let me illustrate how we can use these kind of systems to create a similar band structure that we can get using topological insulators. So let me introduce these pieces, spin-orbit coupling and Zeeman field, one at a time. Okay. So let's start by just thinking about the band structure for a wire without spin-orbit coupling at all. So in that case, we just get degenerate parabolas, one for spin up, one for spin down. That's the same problematic picture I drew there. If you turn on spin-orbit coupling, then your spin degeneracy gets partially lifted. So in particular, the spin up branch will, let's say, shift to the right. The spin down branch shifts to the left. All right, so I've just taken the spin up parabola, shifted it rightward, spin down parabola, shifted it leftward. So this, although I've lifted the spin degeneracy, this is not quite what we want, because if you, wherever you put your Fermi level, you always have still two pairs of Fermi points rather than just one. Okay, but here's where the Zeeman field comes in. So if you break time reversal symmetry, then you open up a gap at this crossing, and your band structure then looks something like this. And now you can see that we're in business if you put your chemical potential inside of that magnetic field-induced gap, then you just have a single pair of Fermi points. Okay, so in this sense, we've now achieved a band structure that looks like corresponds to spinless fermions.
Could you please repeat what is step 1 and what is step 2?
So this is spin-orbit coupling, and this is a magnetic field. Okay. So importantly, the carriers at kf and minus kf don't have the same spin. So remember that so the states here basically came from that spin up branch. So electrons at plus kf will be mostly up, but they'll be somewhat polarized by the Zeeman field. And similarly, these guys came from the spin down parabola primarily, and will be mostly spin down again, but again weakly polarized by the field. So in this sense, these two problems are relatively similar in the sense that I have not the same spin species at opposite sides of the Fermi energy. And so the beauty of what I've done here in either strategy is to solve challenges 1 and 2 in a way that makes making these systems superconducting quote unquote easy, right? I'm a theorist, so I shouldn't say it's easy, but yeah.
So for the topological insulators case, you have like Palmer's pair, but in this other case, I presumably the spin is not like they are still like finite over there. Really.
That's right. Yeah. So you can take the extreme case where the Zeeman field is infinite, then you will just perfectly polarize them. But you want to work in the sweet spot where they're still, they're still not parallel, but they have only partially overlapping.
The Basquiat element is basically also partially controlled by those spin states.
Yeah.
Okay.
Yeah.
Excuse me.
Yeah.
So just somewhat trivial question related, but do you call the Z in the nanowire case? So what is the Z direction? Is it outward or along the wire?
Whatever you want.
But and also related, but so do you apply the magnetic field along the wire or perpendicular to the wire?
Yeah, it depends on the spin-orbit interaction. Exactly. So the one thing you don't want to do is, so there's a preferred spin quantization axis dictated by spin-orbit coupling. You want the Zeeman field to be perpendicular to that axis. So the bad direction would be to, if I added the field along the direction in which the spins are already preferentially pointing due to spin-orbit coupling, I would just shift these parabolas vertically, put one up, the other down, and that doesn't do anything for me. All right, so that's step 1. Step 2 is to couple either one of those systems to just whatever your favorite conventional superconductor is, aluminum, niobium, whatever you prefer. So as an example, I'll just use wires, although the idea is more general. So let's suppose you took this one-dimensional wire with Rossby spin-orbit coupling, and I have a magnetic field applied, and then I drop that on an ordinary superconductor. Okay, so when those materials come in proximity to each other, electrons from the wire can tunnel into the superconductor and back, and due to that hybridization, the electrons in that wire will inherit properties that are native to that superconductor. So most importantly, those electrons will inherit the spin-singlet Cooper pairing that originates there. And the key thing is that spin-singlet Cooper pairing can still happen very efficiently because I have both spin-up and spin-down electrons that are available to form singlets at the Fermi energy. Right. So if I just redraw that same picture, if my chemical potential is here, once again I have spin states which are not aligned at kf and minus kf, and so I will inherit by this so-called proximity effect a pairing of those electrons that will gap my system out and take me to a topological superconductor that has Majorana zero modes at the endpoints of the wire. All right, so that's a pretty elegant two-step recipe. The fact that one is working just with rather ordinary materials is a huge virtue, and lots of experiments were kicked off by these realizations. Now, if you're an experimentalist and you think you can make one of these devices, natural question is, what do you measure to tell whether there are actually Majorana zero modes in that system or not? Okay. So that's the question I'd like to turn to next. Question?
So, you put a topological insulator in your superconductor. So, are you trying to make it very thin while you want these topological insulators so that you effectively have enough wire?
Well, here, this is actually a little bit tricky. This is the way in which you would accomplish step 2. You can imagine just putting a superconductor next to the edge. Okay, so those edge states are the thing which is kind of like making your one-dimensional wire, and you want them to inherit superconductivity. The somewhat tricky thing here is that in the device geometry I've drawn, you don't have actually localized Majorana zero modes. You would also need to magnetically gap the adjacent parts of the superconductor in order to trap a zero mode.
Can you comment on how you, so I know you do superconductivity and induce some proximity effect, but I'm just curious, how do we actually model that kind of effect?
Yeah, so the simple-minded thing to do is just imagine writing down a Hamiltonian for your wire, and then taking a Hamiltonian for your superconductor, let's say within the, modeled within the BCS mean fields limit, allow single electron tunneling between those two systems, and you can do perturbation theory if you want, or integrate out more formally the superconducting degrees of freedom, and then you'll see that you generate a pairing, an explicit pairing term in the Hamiltonian for the wire. All right, so let's talk now about detection. I should emphasize that my goal here is going to be very modest. I simply want to outline an experimental scheme for deducing the presence of a Majorana zero mode in these kind of hybrid devices. And I want to distinguish that from the question of reading out the quantum state that's encoded in distant Majorana modes. Right, so the existence of a Majorana zero mode can be inferred with local measurements. Reading out the state of, encoded in distant Majorana modes, that's something that you can't infer by local measurement, and that's something that we'll discuss tomorrow. So for now, we're just going to ask a crude question, is a Majorana there or not? So I'm going to just focus on tunneling experiments, so just transport experiments, which are by far the most commonly deployed techniques that are used to address this question. As a primer, I'd like to describe the physics of what happens when you try to tunnel electrons onto a superconductor, viewed as a scattering problem. Okay. All right, so for now, I want to consider this just a completely ordinary gap superconductor, no Majorana physics whatsoever. I'm going to assume that superconductor is grounded. And I want to introduce a lead, which is held at some low bias voltage V relative to that grounded superconductor. So this is a lead. And so when I bias the lead relative to that grounded superconductor, I send in electrons towards that superconductor. So there's an incident electron. And let's think about the fate of that incident electron as it impinges on the superconductor. By the way, when I say low bias voltage V, I mean low compared to, let's say, the size of the gap for that superconductor. All right, so one possible thing that we should consider is whether that incident electron can enter the superconductor and then make its way to ground. If it did so, then we would be getting some current, right, flowing through the circuit. So can that, this would correspond in scattering language to a transmission process. So can that happen in the present situation? No. Anyone? I agree. Do we all agree that's not going to happen? So there's a gap for unpaired electrons there, and that gap is going to forbid single electrons from making their way through the superconductor towards ground. Okay, so that's not going to happen. All right, so what else can happen to that electron? That's what we have to decide. Well, one thing that can, of course, happen is that the electron can reflect, right, and just come back to you as an electron. I'm going to call that normal reflection. So normal reflection processes don't contribute to any current. Okay. There is, however, a way in which current can actually flow through that superconductor towards ground. So there's another kind of reflection process that can happen here, which is actually special to tunneling onto a superconductor. In particular, there's a so-called Andreev reflection, where that incident electron bounces back, not as an electron, but rather as a hole. Okay. That's Andreev reflection. Okay, so there's a deficit of charge, of course, that I have to keep track of. If that electron is going to come back to me as a hole, there must be two other electrons that exist somewhere in the system. And what happens here is that a Cooper pair, two electrons, can be absorbed into the superconductor. There's no penalty for that, right, because there's a condensate for charge 2e Cooper pairs. And that Cooper pair can then make its way to ground and contribute to a finite current in the circuit. Okay. So what I'm interested in here is the conductance which I'll call G, which is just a derivative of the current that flows to ground with respect to the bias voltage that our lead is held at. So let me write the general expression for this, for what this conductance looks like, and then I'll comment on what it means. So it's 2 times e squared over h times the Andreev reflection probability. Okay, so e squared over h, that may or may not look familiar to you, depending on if you have gone through, Landauer, Whittaker conductance. But this is just a conductance quantum, the basic dimension of conductance, unit of conductance. The Andreev reflection probability appears here because the only way in which you get current is if Andreev reflection processes take place. And this factor of 2 just reflects the fact that every Andreev reflection process adds 2 charges to the superconductor rather than 1. Okay. So that's the meaning of this expression. All right, so all you have to do if you want to make a prediction is extract that Andreev reflection probability. Okay. So how do you do that? Well, this is a problem, it's a variation on a problem that you all have studied ages ago in introductory quantum mechanics. You've solved scattering off of a potential barrier. You can solve the wave functions, get the transmission and reflection coefficients, and exactly the same kind of thing takes place here, except I have a superconductor so that I have 2 kinds of reflection coefficients to keep track of, normal and Andreev reflection. But if you solve for the wave functions of the system, back out the Andreev reflection coefficient, then you're basically done. You have a prediction for what the conductance of that system ought to look like. So in the past, when I've talked about this subject, I would follow this up with some hand-waving description of the results. I decided I'm going to try to do better than that here. I'll see how it goes. I don't know how transparent it will be, but I'm going to try to distill this as much as possible. But I think the end result will hopefully be more satisfying than me just writing down the answer and giving you some partially correct motivation. Also, given how common these tunneling measurements are in studies of topological superconductors, I think it's really worth having a deeper understanding of what's going on under the hood. All right, so now let's explore the case where we actually are tunneling onto not a trivial but a topological superconductor. So here's my topological superconductor. I have a Majorana zero mode, which I'm just going to call gamma. So I want to draw a lead here. So I'm going to describe that lead with just a single fermion field, which I'll call psi of x. And the idea is that when that field has a value between x equals minus infinity and x equals 0, that will correspond to an incoming electron. And when that field has a value between 0 and infinity, that corresponds to outgoing modes. All right, and I'm going to allow that fermion to couple with some amplitude t onto that Majorana zero mode. Okay. By the way, I'm really trying to write down the absolute simplest possible Hamiltonian for the lead and this Majorana mode that captures the physics, and I think this is the way to do it. So the Hamiltonian is going to consist of two pieces. There's just going to be kinetic energy for the lead, and then the term which couples the lead at x equals 0 to the Majorana mode. Okay, so for the lead, I'm just going to have kinetic energy minus IV psi dagger dx psi. So I don't know if this looks familiar or not. This is just the momentum of those carriers as they make their way here and back. And ht takes the form t times gamma times psi of x equals 0. So this is not Hermitian, so I have to add the Hermitian conjugate. And so to get the Hermitian conjugate, I can just subtract psi dagger at x equals 0. Okay, so I don't know if it's clear that this thing is now Hermitian, but if I take the Hermitian conjugate of gamma times psi, that's psi dagger gamma. But I can switch the order of the psi dagger and the gamma at the expense of putting a minus sign, and I can just factor out the gamma. Okay, so this is the first place where I suspect there may be some confusion. So that's the Hamiltonian I want to consider. Yeah.
Why do electrons couple to Majorana modes? Typically in tunneling, electrons couple to other electrons.
Well, the Majorana zero mode operator involves electron operators, right? It's a superposition of electron operators. Good. Okay, so good. So if you want to derive this, what you can do is start microscopically from a term that couples psi of x equals 0 to electron operators in that topological superconductor, and then project those electron operators onto the zero mode subspace, and this is what comes out. It's kind of the only thing that can possibly come out, actually. Okay, more questions about this? So I want to make sure we're all at least comfortable with what I've written here. If you're not, then the next 10 minutes is going to be kind of boring.
Can you say again what HT, how should I think about it?
Well, okay, so I think the right way to think about it is actually what I said a second ago. So let's think about, okay, so more fundamentally, I think you'd be happier if I wrote something like psi dagger of x equals 0 times, let's say, some fermion C1 dagger, which sits at the endpoint of that topological superconductor. Sorry, C1 plus Hermitian conjugate. Okay, so that's an ordinary tunneling term, and everybody would be presumably happy writing that down. But C1 is an operator that involves partly zero-mode physics and partly excited state physics in that topological superconductor. So I want to kind of project away the stuff, the contribution from C1 involving the high energy components, and all that's left actually is the Majorana. And so the projection, I think, more or less has to just have the form C1 goes to gamma, maybe with a factor of 2 for normalization. And well, let's check if I've gotten this right. So I get psi dagger of x equals 0 times gamma under this projection, plus Hermitian conjugate, which is gamma times psi of x equals 0. Anti-commute those guys, and that's it. Okay, yeah.
So this is an effective theory for just probing the ground space of the topological superconductor. Is B very small compared to the gap of the topological superconductor?
Yes, I'm assuming. Yeah, so indeed, I'm assuming that I only want to probe energy scales which are small compared to the bulk gap of that topological superconductor. That's what, let's say, justifies me doing this kind of projection.
And not writing down the other Hamiltonian for the topological superconductor.
Yeah, that's right. Yeah. Yeah.
So the upper half of the line is topological superconductor, bottom half is insulator.
You mean this?
No,
Oh, sorry. This is. Let me draw this in a different way. The only reason I drew this in this fashion is that originally I was going to talk about 2D topological superconductors, and then I wanted to have some diagram that captured both at the same time. But I skipped that, so let me just do this. Okay. That's, I think, clear. So apologies about that. So here's our topological superconductor. Okay. Yeah.
Yeah, so we write down this Hamiltonian, we have assumed that we know the existence of the Majorana zero mode. Suppose if we are exploring an unknown system, and we want to show that this system is have this resonant anti-reflection effect, then how do we write down? How do we attack this problem?
Well, I think this is a very, very important question. And so what the philosophy in which I'm trying to do here is I want to try to extract some kind of universal tunneling signatures of a Majorana that would arise if a Majorana zero mode is there. Of course, we need to, just having that signature is not necessarily enough. We also need to compare, let's say, to the response that I would get if this was a trivial superconductor, and we need to compare those two signatures, right? So I have one prediction. Well, we'll get a prediction for the topological case. We should contrast how that looks in the trivial case. Hopefully, those things look very different, qualitatively different. If they don't, then we're in big trouble. If they do look qualitatively different, then we're in business, and we have a good signature to go search for. Now, in practice, I'll say this tomorrow, but it's actually not so simple to distinguish a true Majorana zero mode from some kind of accidental low energy mode which might happen to be sitting at the interface. And that's, I think, one of the key experimental problems in this entire field at the moment.
Are you going to comment on the recent experiment, I guess?
Tomorrow I will, yeah. Yeah.
Split the incoming, should I take this as just really actually like a spin split wire? The incoming and out, the incoming and outgoing is really just a single wire with left moving and right moving.
Exactly. I just have a single right mover, single left mover, so you can indeed imagine that it's spin split. And the only reason I'm doing this is that I'm trying to get the simplest possible description of this.
And you want to spin split?
It doesn't really matter too much how exactly. I mean, any way in which you get a single
You
channel.
want to simplify it so the signature is not maybe associated with some other physics.
We could have kept track of spin here. It would make the problem unpleasantly more difficult. but the results actually don't change. But this is an example of the kind of thing that we would want to make sure about, because odds are the experiment will not actually be done with exactly this kind of perfectly spinless lead. Okay, so are we all okay? Okay, so I have another homework assignment for you. I think we presumably all know how to solve for the eigenstates of this kind of Hamiltonian for arbitrary energies. So if I ignore ht for a second, the solutions to this are just plane waves. And ht comes in and basically relating the incoming and outgoing wave functions at x equals 0. So that's I think, a standard thing. I'm not going to do that. Actually, in preparation for this, I spent, I don't know, 10 hours or something solving that problem. It's not so straightforward. I probably could have done it more efficiently, but it takes some effort to get it right. I'm not going to, as I said, I won't do that in real time. Instead, I'm going to just look at two extreme limits that I think we can back out with some intuition without going through some gory calculation. All right, so specifically, I want to think about the limits where the energy of the incoming electrons is both very large compared to the scale set by that Majorana coupling and very small compared to that scale. Okay, so you might naively say that, well, the range of energies I should think about are E much greater than T and E much less than T. That's actually not a sensible statement. T actually doesn't have units of energy. Okay, so it's dimensionally not correct. And you can just do dimensional analysis and convince yourself of that. So the thing that actually has units of energy is T squared divided by V. I won't just homework exercise, show that that indeed has units of energy. Okay, so I want to look at E much greater than T squared over V and E much less than T squared over V. So in both of those limits, we can make certain simplifications to uncover the physics pretty efficiently. All right, let's start out at E much greater than T squared over V. All right, so the energy for the incoming electrons is much larger than whatever this perturbation does for us.
Can I just clarify?
Yeah.
I'm a little bit confused. So when that integral over x, did you unfold that wire, and so it's really just only one in the unfolded picture, just one kind of a, let's say, right mover, and then you're hopping off that wire, and then x is going from minus to plus infinity, or is that integral has sides have both left and right, and you're integrating from like minus?
Yeah, so I'm integrating indeed from minus infinity to plus infinity. So in the usual right and left moving picture, so psi of x between minus infinity and 0 would be what you might want to call psi right. And then psi from 0 to plus infinity would be psi left. And so I've just incorporated both the right and left mover into a single field, which is, it makes things much more compact.
Just moves in one direction.
Well, depends on. I'm viewing this as a fermion that kind of bends around on itself. I mean, I still need incoming and outgoing modes.
So that's just
It's just distinguished by x, exactly.
The actual psi in there is, the kind of a more correct pictures. Like, if you physically represented that Hamiltonian, you would just be a wire just moving in one direction.
Exactly, it's just a wire.
Onto this superconductor.
That's right. Yeah. Exactly. So the physical coordinate for my wire would just range from, let's say, minus infinity to 0.
Right.
But it's just convenient to lump those right and left movers into it. And really, the only thing I gain from that is that the lead Hamiltonian is a bit simpler, and also this is a bit simpler because I don't have to keep track of these R and L labels.
Right. I just mean like that guy doesn't have, that Hamiltonian no longer has right and left movers. I mean, there are
Only implicitly.
implicitly, you just identify by what x you're at.
Exactly.
Just because it's only plus v, not minus v.
Exactly.
It's not like there's two Fermi points.
Exactly. Yeah. Okay, so can anyone suggest a nice simplification I can make when the incoming energy is much larger than t squared over v? I'm trying to be as crude as possible here, so keep that in mind. So I want to make a simplification of the Hamiltonian. Maybe I'll be more precise. Okay, let's do perturbation theory in t squared over v. I want to do zeroth order perturbation theory. Okay, I want to just kill ht altogether. Okay, so that's the zeroth order thing you can do. So h is approximately h lead in this regime. So this is a problem we can all solve immediately. Right? So this is just kinetic energy. The eigenstates are plane waves. You can just get the eigenstates by passing to momentum space. And those plane wave eigenstates will be created by operators f, fe dagger, which is just integral on x e to the I over v times x times psi dagger of x. So this just creates a plane wave. This is just the plane wave function. Okay, so it's somewhat useful to plot the. Oh, by the way, is everybody okay with this? This is basically just a Fourier transform, right? E over v is just momentum, so this is just a plane wave eigenstate. So if we look at the electron part of the wave function, this absolute value, then it's just constant for all x. Right? That's the electron part. There's no whole part. In other words, there's no psi of x that appears here. So the whole part of the wave function is just 0. Which basically tells us that if an electron comes in, then an electron is going to come out. Right? There's no Andreev reflection that happens whatsoever. Okay, so that instant electron just normally reflects. And then the limit that we're considering so far, basically the lead and that Majorana mode just decouple from each other. Okay. So what we learn is that the conductance, if you probe the system at energy scales which are much greater than t squared over v, is basically 0. All right, so that's not especially interesting, but that's what we find in this regime where we probe the system at relatively high energies. Okay, so I'm out of time, but let me take questions, and we'll go over the more non-trivial case where E is much less than t squared over v next time. Go ahead.
It's really short. This t squared over v, I can think about something like the width of the Majorana.
Yes.
Right?
Yeah.
That's why if I'm away from it, I don't see it.
Exactly. Yeah. And we'll comment on that next time. Another yeah. Yes, exactly. Yeah. So I'm still. My whole theory only makes any sense when we're at energies which are small compared to that. Okay. Any other questions for now? Okay. Well, thanks everybody.